The autumn rain drummed against the corrugated roof of Hangar 7, somewhere in the industrial outskirts of Hamburg. Inside, under the harsh glare of wartime floodlights, a dozen German engineers stood in a semicircle around what looked like the remains of a shattered violin. The object before them defied everything they thought they knew about modern aviation. It was October 1943, and the Third Reich's finest technical minds had gathered to examine the wreckage of a British aircraft that had been terrorising German airspace for nearly 2 years. The plane lay disassembled on wooden sawhorses, its pale surfaces reflecting the electric lights like polished furniture. To men accustomed to the brutal geometry of steel and aluminum, the sight was almost offensive in its elegance. Dr. Wilhelm Strauss adjusted his wire-rimmed spectacles and approached the largest section of fuselage. He had spent 15 years analysing metal fatigue in aircraft structures, studying the stress patterns that spelled life or death for German pilots. Yet here before him was something that challenged every principle he held sacred about aeronautical engineering. The aircraft was a de Havilland Mosquito, and it was made almost entirely of wood. Strauss tapped the surface with his knuckles, producing a hollow resonant sound that echoed through the hangar. Around him, his colleagues exchanged glances that mixed skepticism with grudging curiosity. For months, intelligence reports had described this phantom bomber that appeared over German targets faster than any interceptor could catch it. Now they could finally touch the mystery that had been humiliating their air defences. The Mosquito had crash-landed in a farmer's field near Bremen after taking heavy flak damage during a precision raid on a submarine pen. Miraculously, the wooden structure had absorbed the impact without shattering completely, giving German recovery teams their first intact example of what British propaganda called the wooden wonder. As Strauss examined the wreckage more closely, he noticed something that made him frown. The wood panels weren't simply nailed or bolted together like the crude plywood trainers he remembered from his early flying days. Instead, they appeared to be fused into a single continuous surface, as smooth as carved marble. The joints between layers were invisible to the naked eye. His assistant, a young engineer named Heinrich Müller, pointed to a section where the impact had exposed the internal structure. Layer upon layer of thin wood veneer was visible in cross-section, alternating grain directions like the pages of a book. Between each layer was a dark line that looked almost like dried honey. "Herr Doctor," Müller said quietly, "what kind of adhesive could create bonds this strong?" Strauss had been wondering the same thing. In German aviation, wood construction meant casing glue derived from milk proteins. It was cheap and adequate for training aircraft, but it degraded in moisture and heat. This British bonding agent appeared to be something entirely different. When he attempted to separate 2 layers with a steel chisel, the wood fibre itself split before the glue line gave way. The implications were staggering. If the British had developed an adhesive stronger than the wood it bonded, they had essentially created a new class of material. Not wood, not metal, but something hybrid that combined the best properties of both. Dr. Ernst Keller, the hangar's chief metallurgist, approached with a fragment he had been studying under magnification. His expression carried the bewildered look of a man confronting something beyond his expertise. "The bonding appears to be molecular," he announced to the group. "Whatever compound they're using, it penetrates deep into the wood fibres and hardens into something resembling synthetic resin. I've never seen anything like it." The assembled engineers fell silent. Germany's chemical industry had produced synthetic rubber, artificial fuel, and countless other marvels of wartime innovation. Yet somehow, British furniture makers had created an adhesive that German laboratories couldn't identify. As the night wore on, the team methodically catalogued every component of the wreckage. They measured, weighed, and photographed each section with the thoroughness of archaeologists examining ancient artifacts. What they discovered challenged every assumption about aircraft construction. The Mosquito's fuselage consisted of just 2 major components, each moulded as a complete half and then joined along the centre line. There were no internal frames, no complex assemblies of ribs and stringers. The wooden shell itself provided all the structural strength, creating an incredibly light yet rigid airframe. The wings revealed even more sophisticated engineering. Multiple layers of birch plywood sandwiched a core of balsa wood, creating a structure that was both incredibly light and remarkably strong in bending. When Strauss calculated the strength-to-weight ratio, the numbers seemed impossible. The wooden wing was actually lighter than an equivalent aluminum structure, while maintaining comparable load-bearing capacity. But it was the manufacturing technique that truly amazed them. Instead of the thousands of individual rivets that held German aircraft together, the Mosquito relied entirely on its revolutionary adhesive. Every joint, every connection, every critical stress point was bonded rather than mechanically fastened. Muller spent hours examining the cockpit area, where the wooden structure transitioned into metal engine mounts and control surfaces. The integration was seamless, suggesting a level of manufacturing precision that German factories, operating under constant bombing and material shortages, could barely imagine. "They're building these in furniture workshops," Strauss muttered, studying a section that bore the unmistakable marks of handcrafted construction. Piano makers, cabinet builders, craftsmen who've never seen the inside of an aircraft factory. The revelation was both inspiring and deeply troubling. While German aviation relied on massive industrial complexes and specialized metalworking equipment, the British had dispersed production among countless small workshops. Every bombed factory could be replaced by a dozen furniture makers working in village shops across the countryside. As dawn approached, the engineers began to understand that they weren't just examining an aircraft. They were looking at an entirely different philosophy of manufacturing, one that turned scarcity into innovation and transformed traditional craftsmanship into cutting-edge technology. Dr. Strauss picked up a fragment of the mysterious adhesive, now hardened into an amber-like substance. Under the fluorescent lights, it gleamed with an almost organic quality, as if alive with trapped energy. "Gentlemen," he said to his exhausted colleagues, "we need to understand this glue. Until we do, we're fighting an enemy whose weapons we cannot comprehend." Outside the hangar, the war continued its relentless pace. German cities burned under Allied bombing raids, and the Luftwaffe's fuel reserves dwindled with each passing month. But inside Hangar 7, a small group of engineers had discovered something that would change their understanding of what was possible. The British hadn't just built a faster bomber, they had reimagined the very nature of aircraft construction, proving that innovation could emerge from the most unexpected places. And at the heart of their breakthrough was a simple adhesive that bonded wood with a strength that defied explanation. What they didn't yet realize was that unlocking the secret of that glue would lead them down a path of scientific discovery that revealed the true genius behind British wartime engineering. The Mosquito wasn't just a triumph of speed over armour. It was proof that sometimes the most revolutionary advances come not from building bigger or stronger, but from thinking completely differently about the problem itself. The first breakthrough came 3 days later when Dr. Keller's chemistry team finally managed to dissolve a sample of the British adhesive in acetone. Under the microscope, the solution revealed a complex molecular structure unlike anything in German technical literature. The compound appeared to be a phenol-formaldehyde resin, but with modifications that made it far superior to anything German industry had produced. Heinrich Müller worked through the night, cross-referencing the chemical analysis with captured British technical documents. What he found in a water-damaged RAF maintenance manual made him call for Dr. Strauss immediately. The adhesive wasn't just glue in the traditional sense. It was a thermosetting polymer that actually grew stronger under heat and pressure. "Look at this," Müller said, pointing to faded diagrams showing the curing process. "They're not simply sticking wood together. They're creating a chemical reaction that transforms the entire structure into something new." Strauss studied the technical drawings with growing amazement. The British manufacturing process involved heating the bonded wood assemblies in massive ovens, allowing the re-rate deep into the grains into pennet, while simultaneously hardening into an unbreakable matrix. The result was neither wood nor plastic, but a hybrid material that combined the flexibility of timber with the durability of synthetic compounds. The implications were revolutionary. Traditional aircraft construction relied on mechanical fasteners that created stress concentration points where cracks could initiate. The Mosquito's bonded structure distributed loads evenly across the entire airframe, eliminating the weak points that plagued conventional designs. Dr. Franz Weber, a structural analyst who had remained skeptical throughout the initial examination, conducted his own tests on fragments of the wing structure. When he applied loads that should have caused catastrophic failure, the wooden composite simply flexed and returned to its original shape. The material seemed to possess an almost organic ability to absorb punishment and recover. "It's behaving like living tissue," Weber reported to the assembled team. "The wood fibers provide flexibility, while the resin matrix prevents permanent deformation. They've essentially grown an aircraft rather than building one. The manufacturing revelation was equally astounding. Through careful examination of tool marks and surface finishes, the engineers determined that major components had indeed been produced in furniture workshops using traditional woodworking techniques. The British had taken skilled craftsmen who understood the properties of wood and given them a space-age adhesive that transformed their ancient art into modern aviation technology. This distributed manufacturing approach explained how the Mosquito had appeared in such numbers despite the intense bombing of British aircraft factories. While German production remained concentrated in vulnerable industrial complexes, the British had created a network of small workshops that could continue operating even under sustained attack. Strauss requested samples of German woodworking adhesives for comparison testing. The results were humbling. Cassin glue, the standard German compound, failed completely when exposed to the temperature and humidity cycles that aircraft experienced in service. Even under ideal conditions, it provided less than half the bond strength of the British resin. The chemical composition analysis revealed why. The British compound was a true polymer, with long molecular chains that created millions of crosslinks throughout the bonded joint. German Cassin glue relied on much simpler protein bonds that degraded rapidly under stress. It was the difference between a modern synthetic rope and twisted plant fibers. As word of the discovery spread through German technical circles, requests for information poured in from aircraft manufacturers across the Reich. Messerschmitt engineers wanted to know if the bonding technique could be applied to metal construction. Junkers designers inquired about the weight savings possible with wooden primary structures. Even the rocket program at Peenemünde expressed interest in adhesives that could withstand extreme thermal cycling. But reproducing the British achievement proved impossible. Germany's chemical industry was already stretched beyond capacity producing synthetic fuels and explosives. The raw materials needed for phenol formaldehyde resin were in desperately short supply, diverted to more critical military applications. Even if the formula could be replicated, the manufacturing infrastructure simply didn't exist. Dr. Keller's team attempted to create their own version using available German chemicals. Their first prototype adhesive showed promise in laboratory testing, but failed catastrophically when exposed to the vibration and temperature extremes of actual flight. The molecular structure wasn't stable enough to maintain its properties under operational conditions. A second attempt using modified coal tar derivatives produced a resin that hardened properly but remained brittle in cold weather. Test assemblies that performed well at room temperature shattered like glass when chilled to simulate high-altitude conditions. The British had somehow achieved a perfect balance between strength and flexibility that German chemistry couldn't match. Meanwhile, intelligence reports continued to arrive describing Mosquito operations that seemed to mock German defensive capabilities. The wooden bombers appeared over Berlin in broad daylight, dropped their loads with surgical precision, and vanished before interceptors could respond. Each successful mission was a reminder that British innovation had achieved what German engineering excellence could not match. The psychological impact was devastating. For decades, German technical superiority had been an article of national faith. Precision manufacturing, advanced metallurgy, and rigorous engineering discipline were supposed to guarantee victory in any technological competition. Yet here was proof that British furniture with what makers, working appeared to be simple wood and glue, had created something that Germany's finest minds couldn't replicate. Dr. Strauss found himself working 18-hour days, driven by a combination of professional curiosity and national humiliation. Every test, every analysis, every failed attempt to reproduce the British achievement only emphasized how completely German assumptions about aircraft design had been overturned. The wooden Mosquito fragments spread across his laboratory bench seemed to mock decades of German engineering tradition. They represented more than just a successful aircraft design, they were evidence that innovation could emerge from the most unexpected sources, that traditional craftsmanship combined with advanced chemistry could produce results that pure industrial might could not achieve. In his private notes, Strauss wrote what he could never say aloud to his superiors. The British had won not through superior resources or manufacturing capacity, but through the courage to abandon conventional thinking. They had looked at their limitations, shortage of aluminum, dispersed manufacturing base, reliance on skilled woodworkers, and transformed each constraint into an advantage. As winter approached and Allied bombing intensified, the mystery of the Mosquito's glue became a symbol of everything German engineering had failed to anticipate. The secret wasn't just in the chemistry of the adhesive, but in the revolutionary thinking that had made its application possible. The breakthrough that would haunt German engineers for decades came on a frigid December morning when Dr. Strauss received an unexpected visitor. Air Marshal Friedrich von Lossberg arrived unannounced at the Hamburg facility, his staff car crunching through fresh snow as it pulled up to Hangar 7. The visit wasn't social. Intelligence reports from occupied Norway had described something that defied belief. A formation of mosquitoes had struck the heavy water facility at Vemork, flying so low that witnesses claimed they could see the pilots' faces. The wooden bombers had appeared without warning, delivered their payload with surgical precision, and vanished into the fjords before German fighters could even scramble. What troubled von Lossberg wasn't the tactical success. It was the impossible flight profile the aircraft had somehow achieved. They flew through a mountain pass, he told the assembled engineers, his voice tight with controlled frustration. At an altitude where the air should have torn those wooden wings apart, yet every aircraft returned to base intact. Dr. Weber, the structural analyst, looked up from his calculations with obvious confusion. According to his stress models, the dynamic loads encountered during such extreme low-level flight should have exceeded the failure threshold of any wooden structure. The fact that the mosquitoes had not only survived but completed their mission suggested properties that German engineering simply couldn't explain. The answer lay hidden in the molecular structure of that revolutionary adhesive, though it would take weeks of painstaking analysis to understand why. Under extreme stress, the phenol formaldehyde matrix didn't fail catastrophically like traditional materials. Instead, it exhibited what modern engineers would recognize as viscoelastic behavior, absorbing shock loads and distributing them gradually throughout the airframe. Heinrich Müller had been conducting fatigue tests on small samples of the British composite material. His results defied conventional wisdom about wooden structures, where traditional aircraft suffered from cumulative damage that eventually led to failure. The Mosquito's bonded construction seemed to actually strengthen under repeated stress cycles. The resin matrix formed new molecular crosslinks each time it was loaded and unloaded, creating a structure that literally learned from experience. It's as if the material remembers every stress it encounters, Miller reported to von Lossberg during a classified briefing. Each flight makes the structure more resilient, not weaker. We're observing a phenomenon that our textbooks say should be impossible. The implications extended far beyond aircraft design. If the British had indeed created a material that improved with use, rather than degrading, they had fundamentally altered the mathematics of structural engineering. German designers had always calculated safety factors based on progressive deterioration. The Mosquito appeared to operate according to entirely different rules. Dr. Keller's chemistry team had meanwhile identified another crucial component of the British formula. Trace analysis revealed the presence of organic catalysts that controlled the curing process with extraordinary precision. The adhesive didn't simply harden when heated, it underwent a carefully orchestrated chemical transformation that optimized its properties for specific applications. Different sections of the aircraft showed variations in the resin composition that corresponded perfectly to local stress requirements. Wing roots, where bending loads were highest, contained additives that increased flexibility. Fuselage joints, which needed to resist torsional forces, used compounds that maximized rigidity. The British had essentially tailored their miracle glue to match the exact demands of each structural element. This level of sophistication suggested manufacturing capabilities that German industry couldn't match even under peacetime conditions. The precise temperature and pressure control required for such selective curing demanded equipment that German factories, operating under constant air attack and material shortages, simply didn't possess. Von Lossberg's technical staff had been analysing captured British production documents, trying to understand how wooden aircraft could be manufactured with such consistency. What they discovered was a revelation that challenged German assumptions about industrial organisation. The British hadn't centralised mosquito production in massive factories like German aircraft manufacturers. Instead, they had created a network of specialised workshops, each contributing specific components that were assembled at final integration centres. Master craftsmen who had spent decades building fine furniture found themselves shaping wing sections with tolerances measured in thousandths of an inch. Piano makers contributed their expertise in laminated construction, to create fuselage shells that resonated with perfect acoustic properties. Even violin builders played a role, their understanding of how wood responded to stress and vibration proving invaluable in designing control surfaces. This distributed approach meant that bombing a single facility could never cripple Mosquito production. The aircraft emerged from workshops scattered across the British countryside, each one small enough to escape notice but collectively capable of producing hundreds of aircraft per month. It was industrial resilience disguised as cottage industry. The psychological warfare aspect wasn't lost on German commanders. Every Mosquito mission served as a demonstration of British technical superiority that couldn't be hidden from the German public. When wooden bombers appeared over Berlin in broad daylight, citizens who had been promised invincible air defences witnessed proof of their leaders' failures. The aircraft's very existence undermined Nazi propaganda about German technological dominance. Intelligence reports from occupied territories revealed another dimension of the Mosquito's impact. Resistance movements had adopted the aircraft as a symbol of hope, spreading stories of its exploits that grew more legendary with each retelling. The wooden bomber that couldn't be caught became a metaphor for the possibility of defeating an apparently invincible enemy through cleverness rather than brute force. Dr. Strauss found himself obsessing over manufacturing details that his superiors considered irrelevant. How had British quality control maintained such consistency across hundreds of small workshops? What training programs had transformed furniture makers into precision aircraft builders? The answer suggested an approach to industrial management that German hierarchical systems couldn't accommodate. British technical manuals revealed a philosophy that emphasized worker initiative rather than rigid adherence to procedures. Craftsmen were encouraged to suggest improvements based on their hands-on experience. This bottom-up innovation contrasted sharply with German practices, where design decisions flowed strictly from engineering offices to production floors. The result was continuous refinement that kept the Mosquito ahead of German countermeasures. Wind tunnel tests conducted at the Aerodynamische Versuchsanstalt in Göttingen confirmed what combat reports had suggested. The Mosquito's wooden construction created aerodynamic properties that metal aircraft couldn't match. The organic surface absorbed boundary layer turbulence in ways that reduced drag while maintaining control authority at extreme angles of attack. It was as if the aircraft had been designed by nature rather than engineers. The discovery prompted frantic efforts to develop German wooden aircraft using available materials and adhesives. Prototype programs at Junkers and Heinkel attempted to replicate British techniques using indigenous resources. Every effort failed catastrophically. German glues couldn't withstand operational stresses, available wood, species lacked the proper grain characteristics, and manufacturing facilities designed for metal construction couldn't adapt to organic materials. One particularly ambitious project attempted to create synthetic wood using compressed paper and German resin. The resulting material looked promising in laboratory tests but disintegrated during the first flight trial. The test pilot barely survived when the wing structure delaminated at 3,000 feet, turning his aircraft into a collection of paper fragments held together by failing glue joints. As 1944 dawned, von Lossberg's intelligence network reported Mosquito variants that pushed the boundaries of what wooden construction should theoretically permit. High-altitude reconnaissance versions flew missions at altitudes where metal aircraft experienced structural fatigue. Night fighters equipped with radar systems that should have been too heavy for wooden airframes dominated nocturnal skies over Germany. Each new variant demonstrated capabilities that German engineering had declared impossible. The final insult came when captured British documents revealed production costs for the Mosquito program. Despite using advanced adhesives and requiring skilled craftsmanship, wooden bombers could be manufactured for less than half the cost of equivalent metal aircraft. The British had achieved superior performance while reducing both material consumption and manufacturing complexity. Dr. Strauss compiled his final report on the Mosquito investigation in February 1944. The document, classified at the highest levels, concluded that German aviation had fundamentally misunderstood the relationship between materials science and structural design. The British had proven that advanced chemistry could transform traditional materials into substances with properties that exceeded the best metal alloys. His recommendations called for immediate development of German synthetic resins, establishment of woodworking training programs, and complete revision of aircraft design philosophy to emphasize flexibility over rigidity. Every suggestion was quietly ignored by superiors, who couldn't admit that furniture makers had surpassed German engineering excellence. In his private laboratory, surrounded by fragments of the wooden bomber that had revolutionized warfare, Strauss understood that he was witnessing more than military defeat. The Mosquito represented a new approach to technological development that valued innovation over tradition, adaptability over standardization. It was a lesson that would reshape post-war aviation, though Germany would pay a terrible price for learning it too late. The glue that held those wooden panels together had become a symbol of everything German industry had failed to anticipate. Stronger than steel, more flexible than aluminum, and manufactured by craftsmen rather than industrial giants, it embodied principles that would define the future of advanced materials. The British had, well, not through superior resources, but through the revolutionary idea that sometimes the oldest solutions, enhanced by the newest science, could achieve what no amount of conventional thinking could accomplish. The spring of 1944 brought disturbing intelligence reports that reached the highest levels of the Luftwaffe command. Mosquito formations were now conducting missions that defied every principle of wooden aircraft limitations. Photos from reconnaissance flights showed the bombers operating at altitudes where the thin air should have stressed their organic structure beyond endurance. Yet they continued to perform with mechanical precision that metal aircraft struggled to match. Dr. Strauss received orders to expand his investigation beyond simple material analysis. The Reich needed to understand not just what the British had created, but how they had overcome the fundamental physics that should have made wooden high-performance aircraft impossible. His team was given access to captured RAF technical manuals, interrogation reports from downed aircrew, and even fragments recovered from Mosquito crashes across occupied Europe. What emerged was a picture of manufacturing sophistication that challenged German assumptions about industrial capacity. The British had developed quality control systems that ensured consistency across hundreds of workshops, while maintaining the flexibility that mass production typically destroyed. Each furniture maker working on Mosquito components received detailed specifications that read more like scientific formulas than traditional blueprints. The adhesive application process alone required 17 distinct steps, each timed to the minute and controlled within precise temperature ranges. Workers used specially designed brushes that applied the resin in specific patterns to maximize molecular bonding. Pressure was applied using pneumatic systems that maintained exact loads throughout the curing cycle. The result was a manufacturing process that combined artisan skill with laboratory precision. Heinrich Müller discovered something even more remarkable in captured production records. The British had established feedback loops that allowed shop floor workers to suggest modifications to both materials and techniques. Improvements identified in one workshop were rapidly disseminated across the entire network through a communication system that functioned with wartime efficiency. German hierarchical structures, where innovation flowed only from engineering offices downward, couldn't compete with this collaborative approach. The phenol formaldehyde resin itself represented a triumph of applied chemistry that German laboratories struggled to comprehend fully. Spectroscopic analysis revealed molecular chains of extraordinary complexity, with cross-linking patterns that created strength in multiple directions simultaneously. Under stress, these chains didn't break catastrophically like conventional materials. Instead, they redistributed loads through pathways that actually increased structural integrity. Dr. Weber conducted exhaustive testing on wing sections recovered from a Mosquito that had crash-landed near Hamburg. His stress analysis equipment, designed for metal specimens, initially gave readings that seemed impossible. The wooden composite absorbed impact energy through mechanisms that no German engineering textbook had described. When loaded beyond theoretical failure points, the material deformed elastically and returned to its original shape without permanent damage. It behaves like muscle tissue, Weber reported during a classified briefing attended by representatives from every major German aircraft manufacturer. The structure adapts to applied loads rather than simply resisting them. They've created an aircraft that learns from the stresses it encounters. This adaptive behavior explained reports from Luftwaffe pilots who described Mosquitoes performing maneuvers that should have resulted in structural failure. The wooden bombers pulled through high G turns that would have torn the wings off conventional aircraft. They dove at speeds that exceeded design limitations without experiencing flutter or control surface reversal. Each extreme maneuver seemed to strengthen rather than weaken the airframe. The British manufacturing network proved equally resilient under investigation. German intelligence identified over 300 workshops contributing to mosquito production, from major furniture factories in High Wycombe to village cabinet shops in remote Scottish Highlands. This distributed system meant that destroying any single facility had minimal impact on overall output. The aircraft industry had become virtually impossible to target effectively. Quality control mechanisms that maintained precision across this dispersed network represented organisational innovation that German administrators found difficult to understand. British production supervisors moved constantly between workshops, carrying portable testing equipment that verified material properties and assembly tolerances. Any deviation from specifications triggered immediate corrective action that prevented defective components from entering the supply chain. The training programs that transformed furniture makers into aircraft builders operated on principles that challenged German educational philosophy. Rather than extensive theoretical instruction followed by practical application, British workers learned through hands-on experience guided by master craftsmen who understood both traditional woodworking and advanced aviation requirements. This apprenticeship model produced skilled technicians faster than formal engineering schools. Dr. Keller's chemical analysis team made another discovery that highlighted German industrial limitations. The British resin system included stabilizing compounds that prevented degradation under ultraviolet radiation, temperature, cycling, and chemical exposure. German adhesives, formulated primarily for indoor furniture applications, failed rapidly when exposed to operational environments that aircraft routinely encountered. Creating equivalent compounds required raw materials that German chemical plants could no longer obtain due to Allied blockades. The specific catalysts that controlled resin curing came from tropical plants that grew only in territories now under British control. Even if German chemists could synthesize alternatives, the production capacity needed to supply aircraft manufacturers simply didn't exist within the Reich's strained industrial infrastructure. Wind tunnel testing at Göttingen revealed aerodynamic properties that challenged fundamental assumptions about surface materials and airflow behavior. The mosquito's wooden skin interacted with boundary layer air in ways that reduced drag coefficients below values achieved by polished metal surfaces. Microscopic examination showed that wood grain patterns created beneficial turbulence that actually improved control authority at high angles of attack. These discoveries prompted desperate attempts to incorporate wooden components into German aircraft designs. Messerschmitt engineers experimented with laminated wing panels that might reduce weight while maintaining structural integrity. Focke-Wulf designers investigated wooden control surfaces that could provide better aerodynamic efficiency than aluminum alternatives. Every experiment failed when subjected to operational testing. The fundamental problem wasn't technical knowledge, but industrial philosophy. German manufacturing had evolved around precision metalworking that demanded rigid specifications and exact tolerances. Wooden construction required understanding of organic materials that varied with humidity, temperature, and grain characteristics. German factories lacked both the equipment and expertise needed to work effectively with such variable substances. Meanwhile, combat reports continued documenting mosquito capabilities that seemed to mock German defensive preparations. Formation flights appeared over heavily defended targets with timing precision that suggested navigation systems more accurate than anything German technology had achieved. The wooden bombers struck with surgical accuracy that minimized collateral damage while maximizing military impact. Intelligence analysts recognized the psychological warfare dimension of these demonstrations. Each successful Mosquito mission proved to German civilians that their air defenses had become ineffective against determined attackers. The aircraft's very existence undermined Nazi propaganda claims about technological superiority and industrial invincibility. Wooden bombers built by furniture makers had become symbols of German engineering failure. Von Lossberg's staff compiled production statistics that revealed the true scope of British achievement. Despite requiring skilled craftsmanship and advanced materials, Mosquito manufacturing costs remained significantly below those of equivalent metal aircraft. The British had proven that sophisticated engineering could actually reduce rather than increase production complexity when applied intelligently to available resources. The implications extended beyond immediate military applications. Post-war aviation would inevitably incorporate lessons learned from wooden bomber development. Advanced adhesives would enable composite structures that combined multiple materials for optimized performance. Manufacturing techniques that emphasized worker skill rather than machine precision would prove valuable in peacetime industries requiring flexibility and innovation. Dr. Strauss found himself documenting not just technical specifications, but an entirely different approach to problem solving that German culture seemed incapable of adopting. The British had embraced uncertainty and variability as design parameters rather than obstacles to overcome. They had created systems that thrived on adaptability rather than demanding rigid control of every variable. His final reports, circulated only among the highest levels of German command, concluded that the Mosquito represented more than superior aircraft design. It embodied industrial and cultural advantages that couldn't be replicated through engineering effort alone. The British had integrated traditional craftsmanship with advanced science in ways that produced results exceeding what either approach could achieve independently. As Allied bombing intensified throughout 1944, mosquitoes continued appearing over German targets with impunity that highlighted the Reich's technological decline. The wooden bombers that had once seemed like desperate improvisation now revealed themselves as sophisticated weapons that outclassed anything German industry could produce. Their success proved that innovation often emerged from constraint rather than abundance, that limitations could become advantages when approached with sufficient creativity and determination. In laboratories across Germany, fragments of captured mosquito structure remained under constant analysis, their secrets gradually yielding to scientific investigation. Yet understanding the technical achievement couldn't bridge the gap in industrial capability and cultural approach that separated German engineering from British innovation. The glue that bonded those wooden panels together had become a symbol of everything the Reich had failed to anticipate about the changing nature of technological competition. The wooden bomber continued its missions, each flight a demonstration that sometimes the most revolutionary advances came not from building bigger or stronger, but from thinking completely differently about fundamental assumptions. The furniture makers had taught the world that strength could emerge from flexibility, that traditional materials enhanced by advanced chemistry could achieve what no amount of conventional engineering could accomplish. The autumn of 1944 brought reports that shattered what remained of German confidence in their air defences. Mosquito squadrons were now conducting operations that redefined the boundaries of wooden aircraft performance. Night fighter variants equipped with radar sets that should have been prohibitively heavy for organic construction dominated the skies over the Reich. Each mission proved that British engineers had transcended the limitations that German theory insisted were absolute. Dr. Strauss stood before a collection of fragments that represented the evolution of British wooden aircraft technology. Pieces recovered from different Mosquito variants showed progressive refinements that suggested a manufacturing system capable of continuous improvement while maintaining production volume. The adhesive formulations had evolved, becoming more sophisticated with each generation of aircraft. Chemical analysis revealed that the British were now using multiple resin compounds within single aircraft, each optimized for specific structural requirements. Wing sections contained flexible polymers that absorbed gust loads without transmitting shock to the fuselage. Engine mounts used rigid formulations that transferred power efficiently while damping vibration. The cockpit area employed fire-resistant variants that maintained integrity under extreme heat. This selective application of different adhesive systems required manufacturing precision that German workshops could never achieve under wartime conditions. Each joint demanded specific temperature and pressure cycles timed to molecular precision. British quality control had somehow maintained these exacting standards across hundreds of production facilities, while German factories struggled to maintain basic consistency with simpler metal construction techniques. Heinrich Müller discovered documentation that revealed the true scope of British industrial innovation. Training programs had transformed traditional craftsmen into specialists who understood both organic chemistry and structural mechanics. Furniture makers could now calculate stress distributions and molecular bonding patterns with accuracy that rivaled university-trained engineers. The British had created an entirely new category of skilled worker. The educational approach challenged fundamental German assumptions about technical knowledge. Rather than separating theoretical understanding from practical application, British training integrated both aspects from the beginning. Craftsmen learned why specific adhesive formulations worked, while simultaneously developing the manual skills needed to apply them correctly. This combination produced workers who could adapt techniques to solve unexpected problems. Dr. Weber's structural testing had identified another revolutionary aspect of Mosquito design. The wooden airframe didn't simply resist applied loads, it channeled stress through pathways that actually strengthened critical joints. Each flight cycle created microscopic changes in the resin matrix that improved fatigue resistance rather than degrading it. The aircraft literally grew stronger through operational use. This self-improving behavior explained combat reports that seemed to defy engineering logic. Mosquitoes returned from missions with damage that should have caused progressive structural failure, yet continued flying without apparent degradation in performance. The wooden construction absorbed battle damage in ways that preserved essential strength while allowing continued operation. Wind tunnel studies conducted at multiple German research facilities confirmed aerodynamic advantages that metal construction couldn't match. The organic surface texture created beneficial airflow patterns that reduced drag while improving control response. At high angles of attack where metal aircraft experienced severe performance penalties, wooden construction maintained smooth airflow attachment that preserved handling characteristics. These discoveries prompted increasingly desperate German attempts to replicate British techniques using available materials. Research programs investigated synthetic wood created from compressed agricultural waste, adhesive systems based on coal tar derivatives, and manufacturing processes adapted to existing industrial infrastructure. Every effort produced disappointing results that highlighted the gap between understanding principles and implementing practical solutions. The fundamental challenge wasn't technical knowledge but systemic approach. German industry had evolved around standardization and mass production that demanded identical components produced with mechanical precision. Wooden construction required accommodation of natural variation in materials, flexible manufacturing processes that could adapt to changing conditions, and quality control systems that emphasized performance over conformity to specifications. British production networks demonstrated organizational resilience that German planners found difficult to comprehend. Intelligence reports described workshops continuing operations despite repeated bombing attacks, with production simply shifting to alternative locations without significant interruption. The distributed manufacturing system had created redundancy that made the entire network virtually impossible to disable through conventional military action. The psychological impact of continued Mosquito operations extended beyond military considerations. German civilians who witnessed wooden bombers appearing over defended cities understood that their leaders' promises of invincible air defences had proven hollow. Each successful mission demonstrated British technological superiority that Nazi propaganda couldn't explain or counter effectively. Air Marshal von Lossberg's intelligence staff compiled operational analyses that revealed the true scope of Mosquito effectiveness. Mission success rates exceeded 90%, with aircraft losses so minimal that crew survival statistics approached peacetime training levels. The wooden bomber had achieved operational invulnerability that German interceptors couldn't penetrate consistently. Combat footage recovered from gun cameras showed German fighters attempting to engage Mosquito formations, with results that bordered on futile. The wooden bombers accelerated beyond pursuit range while maintaining formation discipline that suggested pilot confidence in their aircraft's capabilities. Luftwaffe pilots reported that engaging Mosquitoes felt like chasing shadows that dissolved whenever interception seemed possible. Dr. Keller's analysis of adhesive samples revealed molecular structures of extraordinary sophistication. The British had developed polymer chains that exhibited different properties under varying stress conditions. Light loads were absorbed elastically, allowing normal operational flexibility. Extreme stresses triggered hardening responses that increased strength exactly when needed most. The material behaved like biological tissue that adapted to environmental demands. This adaptive behavior required understanding of polymer chemistry that German research had never pursued. British scientists had apparently recognized that synthetic materials could exhibit properties more sophisticated than simple strength or flexibility. They had created substances that responded intelligently to applied conditions, changing their characteristics to optimize performance automatically. Manufacturing techniques that produced such sophisticated materials demanded equipment that German factories couldn't replicate. Precision temperature control, exact pressure application, and timing accuracy measured in seconds required industrial infrastructure that operated far beyond German wartime capabilities. The British had invested in manufacturing technology that treated adhesive application as a science rather than a craft. quality assurance systems that maintained consistency across distributed production networks represented organizational innovation that German administrators couldn't duplicate. British supervisors possessed portable testing equipment that verified molecular bonding strength, material homogeneity, and structural integrity at every stage of assembly. Any deviation from specifications triggered immediate corrective action that prevented defective components from compromising aircraft safety. Training documentation captured from British facilities revealed educational philosophies that challenged German technical instruction methods. Workers learned through progressive skill development that integrated theoretical knowledge with hands-on experience from the beginning. This approach produced craftsmen who understood why specific techniques worked, rather than simply following prescribed procedures mechanically. The apprenticeship model that prepared furniture makers for aircraft construction operated on principles that emphasized problem-solving ability over rote memorization. British workers could modify techniques to accommodate material variations, environmental conditions, and production requirements that differed from standard specifications. This flexibility enabled manufacturing systems that maintained quality while adapting to changing circumstances. Intelligence reports documented Mosquito variants that pushed wooden construction into applications that German engineers had considered impossible. High-altitude reconnaissance aircraft operated in atmospheric conditions where organic materials should have suffered dimensional instability. Naval variants exposed to marine environments maintained structural integrity despite humidity and salt exposure that degraded conventional wooden construction. Each new application demonstrated British understanding of material science that exceeded German theoretical knowledge. The wooden aircraft weren't simply successful despite their organic construction. They achieved superior performance because of intelligent material selection and application. British engineers had recognized that advanced chemistry could transform traditional substances into materials with properties that surpassed the best metal alloys. Production statistics revealed economic advantages that compounded military effectiveness. Despite requiring skilled labor and sophisticated materials, Mosquito manufacturing costs remained significantly below those of equivalent metal aircraft. The British had proven that advanced engineering could reduce rather than increase production complexity when applied intelligently to available resources. Dr. Strauss compiled his observations into reports that circulated among German technical leadership with conclusions that challenged fundamental assumptions about industrial development. The British had achieved technological superiority not through superior resources or manufacturing capacity, but through innovative approaches that transformed limitations into advantages. The wooden bomber program represented systematic thinking that integrated materials science, manufacturing engineering, and operational requirements into comprehensive solutions. Rather than accepting constraints as obstacles to overcome, British designers had embraced limitations as parameters that guided creative problem-solving toward unexpected breakthroughs. As German cities continued suffering under Allied bombing campaigns that Mosquitoes guided with surgical precision, the wooden aircraft became symbols of technological revolution that transcended immediate military applications. The furniture makers had demonstrated that innovation emerged from the intersection of traditional craft knowledge and advanced scientific understanding. The glue that bonded those wooden panels together carried implications that extended far beyond aircraft construction. It represented proof that revolutionary advances often came not from building bigger or stronger, but from thinking completely differently about fundamental relationships between materials, manufacturing, and performance requirements. In laboratories across the Reich, scientists continued analysing fragments of British wooden aircraft with growing recognition that they were witnessing the emergence of entirely new approaches to engineering problems. The Mosquito had proven that sometimes the most sophisticated solutions appeared deceptively simple, that true innovation often involved rediscovering ancient wisdom, enhanced by modern knowledge. The war would end with German engineers still struggling to understand fully what British craftsmen had achieved in furniture workshops scattered across the English countryside. The wooden wonder had become more than a successful aircraft design. It embodied principles that would reshape post-war technology development and demonstrate that creativity could triumph over conventional thinking when guided by scientific understanding and manufacturing excellence. The winter of 1945 brought a sense of grim finality to the research facilities scattered across what remained of the Third Reich. In Hangar 7, Dr. Strauss stood amid the accumulated evidence of 4 years spent trying to unlock the secrets of British wooden aircraft technology. The fragments of mosquito structure that covered his laboratory tables represented more than failed attempts at reverse engineering. They were testament to a fundamental shift in how warfare itself was conceived and executed. The final intelligence reports arriving from the collapsing front lines painted a picture of complete mosquito dominance that defied every principle German aviation had held sacred. Wooden bombers were now conducting missions deep into Reich territory with such casual efficiency that Luftwaffe commanders had stopped attempting interception. The aircraft appeared, struck their targets with surgical precision, and vanished before defensive systems could even respond. Heinrich Müller had spent months analysing production data captured during the retreat from occupied territories. What he discovered challenged every assumption about industrial capacity and manufacturing efficiency. British furniture workshops were producing mosquito components at rates that exceeded German metal aircraft factories, despite using what appeared to be traditional craftsmanship techniques enhanced by revolutionary chemistry. The quality control systems that maintained precision across hundreds of small workshops represented organisational innovation that German hierarchical structures couldn't accommodate. British production supervisors possessed authority to modify techniques based on local conditions while maintaining overall performance standards. This flexibility enabled rapid adaptation to changing requirements without compromising structural integrity. Dr. Weber's final structural analysis revealed properties that seemed to violate fundamental engineering principles. The wooden composite material exhibited behaviour that changed depending on loading conditions, becoming more flexible under light stress, and progressively stiffer as loads increased. This adaptive response provided optimal characteristics for every flight regime without requiring complex mechanical systems. The adhesive chemistry that enabled such sophisticated behaviour represented advances in polymer science that German research had never anticipated. Molecular analysis showed cross-linking patterns that created strength in multiple directions simultaneously, while maintaining elasticity that absorbed shock loads without permanent deformation. The material literally learned from operational experience, becoming more resilient with each stress cycle. Manufacturing techniques that produced such consistent results across distributed production networks demanded understanding of process control that German industry had never developed. British craftsmen worked with temperature and pressure tolerances measured in fractions of degrees and pounds per square inch, achieving precision that rivaled laboratory conditions in workshop environments that appeared deceptively simple. The training programs that transformed furniture makers into aircraft builders operated on educational principles that challenged German technical instruction methods. Workers learned through progressive skill development that integrated theoretical knowledge with hands-on experience from the beginning. This approach produced craftsmen who could solve unexpected problems rather than simply following prescribed procedures. Intelligence reports from the final months of war documented mosquito operations that seemed to mock German defensive capabilities. Formations appeared over Berlin during important government meetings, their timing so precise that observers suspected intelligence networks, providing real-time information. The wooden bombers had become instruments of psychological warfare that demonstrated Allied technological supremacy with every mission. The economic implications of British wooden aircraft success extended beyond immediate military considerations. Production costs that remained below those of conventional metal construction, while achieving superior performance, suggested manufacturing philosophies that could revolutionize post-war industry. Advanced materials didn't necessarily require expensive production processes when applied intelligently to appropriate applications. Dr. Keller's chemical team had identified adhesive formulations that incorporated compounds completely unknown to German science. The British had apparently developed synthetic resins that exhibited properties more sophisticated than simple strength or flexibility. These materials responded to environmental conditions by changing their characteristics to optimize performance automatically. Quality assurance systems that verified molecular bonding strength at every assembly stage represented testing capabilities that German facilities couldn't replicate. British workshops possessed portable equipment that analysed material properties with accuracy that rivaled university laboratories. Any deviation from specifications triggered immediate corrective action that prevented defective components from entering the supply chain. The distributed manufacturing network that produced mosquitoes demonstrated resilience that conventional industrial thinking couldn't achieve. Bombing attacks that destroyed individual workshops simply shifted production to alternative locations without significant interruption. The aircraft industry had become virtually impossible to disable through traditional military action. Combat footage from the final air battles over Germany showed Mosquito formations operating with confidence that bordered on casual indifference to German defensive efforts. The wooden bombers maintained precise formations while executing maneuvers that should have stressed their organic construction beyond endurance. Each mission proved that British engineers had transcended limitations that German theory insisted were absolute. Wind tunnel data collected at multiple research facilities confirmed aerodynamic advantages that metal construction couldn't match. The organic surface texture created beneficial airflow patterns that reduced drag while improving control response at extreme flight attitudes. Wooden aircraft achieved performance characteristics that contradicted fundamental assumptions about surface materials and boundary layer behavior. The psychological impact of continued Mosquito operations had eroded German civilian morale beyond military considerations. Citizens who witnessed wooden bombers appearing over defended cities understood that their leaders' technological promises had proven hollow. Each successful mission demonstrated British superiority that Nazi propaganda couldn't explain or counter effectively. Von Lossberg's final intelligence summary documented operational statistics that revealed the true scope of Mosquito effectiveness. Mission success rates that exceeded 90% with minimal aircraft losses had achieved operational invulnerability that German interceptors couldn't penetrate consistently. The wooden bomber had redefined what was possible in military aviation through revolutionary thinking rather than superior resources. Production documentation captured during the Allied advance revealed manufacturing costs that challenged German assumptions about advanced technology requiring expensive industrial infrastructure. British workshops achieved sophisticated results using equipment that appeared deceptively simple, proving that innovation could emerge from intelligent application of scientific principles rather than massive capital investment. The apprenticeship model that prepared craftsmen for aircraft construction emphasized problem-solving ability over mechanical adherence to procedures. British workers could modify techniques to accommodate material variations and environmental conditions while maintaining performance standards. This flexibility enabled manufacturing systems that adapted to changing requirements without compromising quality. Materials science advances that enabled wooden aircraft superiority represented understanding of polymer chemistry that German research had never pursued. The British had recognized that synthetic compounds could exhibit intelligent behavior that responded automatically to operational conditions. They had created substances that optimized their properties based on applied stresses without requiring external control systems. The fragments of wooden aircraft scattered across Dr. Strauss's laboratory would outlast the Reich itself. As Allied forces advanced through the rubble of German cities, the mystery of that revolutionary adhesive remained unsolved. British furniture makers had achieved what Germany's finest engineers could not replicate, proving that innovation emerges not from industrial might, but from the courage to abandon conventional thinking. The glue stronger than steel had become more than a wartime secret. It was proof that sometimes the most profound breakthroughs come from the most unexpected places, forever changing how humanity approaches the impossible.